Taylor Series Part 3. In this part, we're going to look at three typical types of Taylor Series problems. Starting with the first type, which is one where we need to take all the derivatives. We saw that when we found the Taylor series centered at 0 for sine of x. For this example, let's look at f of x equals the square root of 1 plus x, centered at or about x equals 0. And let's find the third degree polynomial approximation to f of x. So for third degree, that means we're just going to go out to the x cubed term, or stop at the x cubed term. So let's take some derivatives. I like to rewrite the function, and I'm going to put it as 1 plus x to the 1/2 power here to help me take derivatives more easily. Let's find f prime of x, doing a power rule. We don't really need the chain out because the chain out is 1. We'll find f double prime of x, negative 1/4. Times 1 plus x to the negative 3/2. Keep going. Find f triple prime of x, which is 3/8, times 1 plus x to the negative 5/2. And we can stop here. Why do we stop at the x cubed term? That is, why do we stop at the triple prime? Because that's going to give me the coefficient for the x cubed term. And then I need to find the values at 0. So f of 0 is 1 to a power, and 1 to any power is 1. F prime of 0 is 1/2 times 1. F double prime of 0 is negative 1/4 times 1. And f triple prime of 0 is 3/8 times 1. And now we can fill in and find our approximation. So the square root of 1 plus x is approximately f of 0 plus f prime of 0 times x minus 0 minus 1/4 times x minus 0 squared over 2 factorial. Don't forget that extra 2 factorial, plus 3/8 times x cubed over 3 factorial, and we can stop. You don't necessarily need to simplify, but I will, which gives me 1 plus 1/2 x minus 1/8 x squared plus, and then if I do 3 over 8 and then 1 over 1 times 2 times 3, I get 1/16 x cubed. So a follow-up question could be something like, what's the square root of, say, 1.5? Well, I can approximate it by doing the square root of 1 plus 0.5. And this one right here is going to be equal. And then I just plug in 0.5 for every x in my polynomial. Like this. And I will leave this to you to simplify if you want to. So the first type is find all the derivatives and plug in to get our Taylor series. The second type is where we manipulate a known series. For example, I know that the sine of x is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. I also know the sigma notation for it. N equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So what if I asked you to find the Taylor series for the sine of 2x? Well, I could take a lot of derivatives, or I could see that to get from here to here, I can substitute in 2x for every x. But I could also do that into my sigma notation. So n to infinity, negative 1 to the n, and then 2x to the 2n plus 1 over 2n plus 1 factorial. Let's do another one of these, but one that looks a little bit more complicated. What if I want to do x minus sine x over x squared? How could I find this Taylor series centered at 0, also called the Maclaurin series, for this function? Well, let's look at the top on its own. Let's look at x minus sine x. And notice that's x minus sine of x, which I'm going to write out in series form. And if I simplify that, the x's cancel, everything else will change the signs, so I get x cubed over 3 factorial minus x to the 5th over 5 factorial. I'll write another term, plus x to the 7th over 7 factorial. Well, how could I do this with my sigma notation? Okay, well, what happened? Up there, I lost my first term. So I started n equals 1. And then I have negative 1 to the n. I'm going to leave a little space. We'll see why in a second. Because did anything else really change from sine x to x minus sine x, other than I lost the first term? I have x to the 2n plus 1 over 2n plus 1 factorial. Well, what did change? What changed was all of these signs. I went from negative x cubed to positive x cubed, positive x to the 5th to negative x to the 5th. So if I plug in n equals 1, all the terms are correct, but my signs are wrong. But now they're correct if I fix it by changing to the negative 1 to the n plus 1 power. Okay, well, let's look at x minus sine x over x squared now. How do I finish this off? Well, pretty easy. I just divide every single term by x squared. So I get x over 3 factorial minus x cubed over 5 factorial, etc. And how does it affect my general term? Well, the only thing I did was I subtracted 2 from each exponent. So instead of having x to the 2n plus 1, I have x to the 2n plus 1 minus 2, or x to the 2n minus 1. The third type of problem is what I call a numeric problem. It's usually given numbers, sometimes in a table, sometimes other ways. But here's an example. Suppose I have a function, and I don't know what f of x is, but I know some information about it. I know that f of 1 is 2, f prime of 1 is negative 3, and then the nth derivative at 1 is n factorial over n times 2 to the n for all n greater than or equal to 2. And let's write the fourth degree polynomial approximation to f of x, even though we don't know what f of x is. Now, where is my polynomial centered? I don't tell you, but it's implied very, very strongly that we're centered at x equals 1. So I'm going to do the fourth degree polynomial approximation. So f of x is f of 1 plus f prime of 1, so minus 3 times x minus the center, plus, okay, we have to do a little work over here. I know that the second derivative at 1 is going to be, I'll write it up here as f2, parentheses of 1. So I substitute 2 for every n, so I have 2 factorial over 2 times 2 squared, and then x minus 1 squared. But don't forget, we have to divide by 2 factorial. I'll do the same thing for f triple prime when n equals 3. So I have 3 factorial over 3 times 2 cubed times x minus 1 cubed, but don't forget over 3 factorial. And one more, because we're going to the fourth degree, which means we stop at the x to the fourth term. So at n equals 4, we have 4 factorial over 4 times 2 to the fourth times x minus 1 to the fourth, and don't forget over that 4 factorial. And I'll clean this up just a little bit. So we have 2 minus 3 times x minus 1. Those factorials cancel. So we get x minus 1 squared over 2 times 2 squared. You can put those together if you so desire. Next term, my 3 factorials cancel. So I get x minus 1 cubed over 3 times 2 cubed. Final term, 4 factorials cancel, leaving us with x minus 1 to the fourth over 4 times 2 to the fourth. So a follow-up question to this might be, what is an approximation for f of 2? And we'll assume that the series converges at x equals 2. So I plug in 2 for every x. And notice that 2 minus 1, of course, gives me 1, so I'm put a little bit extra information that I might not necessarily need. How I get f of 2 is approximately this value.